Welcome to thermodynamics course. I am Dr. Ravi, working as assistant professor in the Department of Pharmaceutical Engineering, BVR in Narsapur. Today we discuss Unit 4, that is phase equilibria in thermodynamics. So this is the continuation of fourth unit, that is vapor liquid equilibrium, phase equilibrium. Okay, so in the previous classes we have seen up to the fundamentals of vapor liquid equilibrium data, in that different cases and different expressions we have seen. Now here the phase diagram for binary solutions. Now here the binary means, here the phase diagram, binary means two compounds. When the two compounds are which are in a vapor liquid equilibrium, when the two compounds which both are in a mixture, the two compounds are there, that's the reason it's called binary solution. When there are in a two vapor liquid equilibrium, then what are the how the phase diagrams looks like. Okay, in that two different cases are there. First one is the constant pressure equilibria, second one is the constant temperature equilibria. First one will see the constant pressure equilibria. So in this case, first assume two compounds are there in the binary solution, that is A, first compound we are calling A, second compound is B. Okay, here the A is the more volatile than the B, so that A is having a high vapor pressure compared to B. Okay, these generally the vapor liquid equilibrium for binary solutions, the phase diagrams are called boiling point diagrams or TXY diagrams. So we can see here the when you draw the diagram between the vapor liquid equilibrium for binary mixtures, the y-axis the temperature is there, in x-axis mole fractions of A, compound A, because A is more volatile compound. Okay, because of that mole fraction of A compound in the liquid and mole fraction of compound A in the vapor. So for that is on the x-axis. Okay, when you draw the temperature versus mole fractions of compound A in a liquid state and vapor state, we will get the equilibrium curve that looks like this. Okay, for example, when initially the binary solution is there, binary solution is started heating. This is at a constant pressure. Okay, we are discussing it, we are kept the pressure is constant, only raising the temperature. Okay, at constant pressure we are raising the temperature. While raising the temperature, initially at the A state, the binary solution in a liquid state. Well, temperature ranges range up to maybe consider T1 temperature. When at T1 temperature, so this is called, this point is called we can see that first bubble, that is called bubble point temperature. So first the liquid is converted into vapor. Okay, so when you draw the horizontal line, so it touches at C. Okay, so this is I forgot to explain, this bottom curve is called TX curve or bubble point curve. The top curve is the TY curve or dew point curve. Okay, so when you draw a horizontal line at a bubble point, so it touches at B and touches at C. Okay, meaning is the mole fraction of compound A in a liquid state, mole fraction of compound A in a vapor state at C. Okay, so means these two mole fractions are in equilibrium at T1 temperature. means at first bubble point the mole fraction of A in a liquid is less compared to the mole fraction of A in a vapor state. So that's the reason we can see, because this is a 0, this is 1. Okay, so means the x here, when you see the on a tx curve, the x is a some particular value, and but when because but here at C the y is more, but here the x is less, means at the bubble point at T1 degree temperature, for T1 the mole fraction of a compound A in a liquid state is less compared to vapor states. Both are in a equilibrium. Equilibrium means, so we are raising the temperature. When the raising of the temperature, the liquid, the binary liquid is converted into vapor. So because A is more volatile than B, so A is converted into vapor state. Okay. So because we are explaining this diagram with respect to only A point of view, means the compound A point of view only. Okay, so after some time with the raising the temperature, and we kept the temperature, for example, at fixed temperature, and we raised the temperature at that particular temperature, the vapor the vapor state of a compound A and liquid state both are in equilibrium. There is no further change unless you increase the temperature. At that temperature, so the mole fractions of two phases are in equilibrium. There is no further change unless you increase the temperature. Up to that, there are in a like that story. That is called, means, so at equilibrium means there is no driving force to change. Okay, at equilibrium, what is the mole fraction in the liquid of a compound A? What is the mole fraction in the mole fraction in the vapor state of compound A? Okay, so at equilibrium, so like that. So then if you increase further, temperature is raised, for example, raise the temperature up to T2, then dry line, okay, when you dry a line, so here is the this is mole fraction of, for example, we are considering this is a x1, this is y1, this is x2, this is y2. So x2 and y2 both are in a equilibrium. Okay, both are in a equilibrium. So x2 is reduced further and y2 this is y1, this is y2. Okay, so both are in equilibrium. Okay, means, so like we increase the temperature, further increase the temperature, for example at T3 it is called the dew point temperature. Okay, and further increase the temperature means in this curve both the compound A in a both vapor and liquid phase, but after the point H, means after high temperatures the compound A only in a vapor state, there is no liquid state. Okay, initially compound A and the initially at point A the compound A only in a liquid state, there is no vapor state, but after reaching the some bubble point, then the compound A in a both phases, after some until up to reaches H, the compound A reaches compound A in a both phases, but after H no A is there in the liquid phase, everything is converted into a vapor state. That's the reason there is no compound A in a liquid state. Okay, so this is the vapor liquid equilibrium diagram. So whatever the equilibrium data is there, like it means x1 and y1 both are equilibrium. Okay, draw the diagram. So this is called XY diagram. So this is very very important for the in the next semester, which is coming mass transfer. So that's the reason it will be very useful in that. XY diagram means x1, you draw the diagram between the y versus x. So y1 x1. So what is the point is coming? For example, so this is a y1, this is a x1, both are in a equilibrium. This is the point. So in the same way, next point, say next point, like that. So this is called, this graph is called equilibrium distribution curve. Equilibrium distribution curve. So this is looks like this. So this diagonal is represented at y is equal to x at a constant pressure. Okay. So with now at constant temperature only, but constant pressure only. Pressure is not changing, but same system, we increase the pressure and increase the pressure kept constant, that pressure only. That is the P2. Now what is the TXY diagram looks like, and P3 and P4 and P5. What is the represent? With increasing the pressures, the vapor liquid equilibrium data looks like this. Okay, so we can see in a XY equilibrium curve. So that is the P1 at P1 pressure, the XY equilibrium curve looks like this, and this is a P2 at P2 pressure, and this P3, P4 and P5, the equilibrium XY equilibrium curves means mole fraction of mole fraction in a liquid state, mole fraction in a vapor state of a compound A, they both are in a equilibrium. So that equilibrium curve looks like this. Okay. Next state, constant temperature equilibrium. So the constant temperature means we kept the temperature is constant, and increasing the pressure, how the compound A mole fractions are vary in a vapor liquid phase and vapor phase, and reaches to equilibrium state. So that we can see here. Okay. So this is a equilibrium line. This is at equilibrium, A and B are in a equilibrium state. So with increasing the temperature, not increasing the temperature at constant temperature, but at a different increased temperature and kept constant. So how the PXY diagrams looks like. So this is about that. Next one, vapor liquid equilibrium in ideal solutions means, so if you want to what are the properties of a ideal solution which are in a vapor liquid equilibrium. Okay, what are the properties of for example, the vapor liquid equilibrium is there. I mean, what are the condition the ideal solution is required to satisfy the vapor liquid equilibrium? So like the components chemically same and no interaction forces. So if the vapor liquid equilibrium phase is there, so in that the chemically the compounds which are there, binary solution chemically must be same, no interaction forces, and there is no change in volume. If you are adding and removing, there is no change in volume, there is no change in enthalpy, and that must obey the Raoult's law, that is Py bar is equal to Xi into Pi saturated. Okay. Okay, so now consider for an ideal solution made up of components A and B, binary solution. Now x1 plus x2 is equal to 1. Okay, so because that means this is a binary solution, it is behaving as a ideally. So means that then means it has to obey the delta V is equal to 0, delta H is equal to 0, and it has to obey Raoult's law. That's the reason That's the reason apply for the because this is it will has to obey the Raoult's law is Pi bar is equal to Xi into Pi saturated. Okay, so for compound 1 P1 bar is equal to Xi into P1s and P2 bar is equal to X2 into P2s. Okay, the total pressure is equal to P1 bar plus P2. We know this one already. Now substitute that P is equal to, what is the P1? X1, this is a 1, not I. X1 P1s plus X2 P2s. Now P is equal to X1 P1s. So we know already X1 plus X2 is equal to 1. Now X2 is equal to 1 minus X1. Substitute that plus 1 minus X1 P2s. Okay, P is equal to X1 P1s plus, now multiply into the bracket and the P2s minus X1 P2s. Now P is equal to P2s plus comma, take the X1 common in both expressions. Now we will get the P1s minus P2s. Okay, this is the total pressure. Okay, now you applied for the liquid state binary mixture. We applied for the Raoult's law for the liquid state. In vapor state, when you apply that, we will get the P1 bar is equal to Y1 into P. The P2 is equal to P2 bar is equal to Y2. Raoult's law, we are applying Raoult's law for gas state into P. Okay, we already know for liquid state P1 is equal to X1 into P1 saturated. P2 bar is equal to X2 into P2 saturated. In an equilibrium state, both are equal. That's the reason we can equate Y1 into P is equal to X1 into P1 sat. Y2 into P is equal to X2 into P2 saturated. Okay. So from here we can write Y1 is equal to X1 P1 sat by P. Y2 is equal to X2 into P2 sat by P. Okay. Now, so the P1 is the saturated pressure of compound 1 and saturated pressure of compound 2 P2. Now ratio of these two are represented as alpha, that is relative volatility. Relative volatility, that is P1 sat by P2 sat. Okay, the alpha is represented the relative volatility. So now divide the x1 by x2. X1 by x2 is equal to x1 P1 sat by P total by x2 P2 sat by P. So P1 get cancelled. Now we will get the x1 P1 sat by x2 P2 sat. Okay, P1 by P2 alpha. Okay, now y1 by y2 is equal to x1 by x2 alpha. Okay, y1 by y2 is equal to x1 by x2 alpha. Okay, now y2 we can write y1 by y1 1 minus y1 is equal to this alpha is there, x1 by x2 alpha. So by simplifying this only get the y1. So how will get so this is after this. So how we will get initially it is there y1 y1 by 1 minus y1 is equal to x1 by x2. X2 we can write x2 alpha is there. Okay, we are writing y1 by 1 minus x1, x1 by 1 minus this x2 also you can write in 1 minus x1 into alpha. Okay, so y1 is equal to x1 by 1 minus x1 into alpha, and this is 1 minus y1. Okay, when you division into that side is will be when you take that division into that side, that will be multiplied with the next term. Okay, now y1 is equal to, so this multiply this term, this whole term to inside the bracket, then we'll get the x1 into alpha by 1 minus x1 minus second term. So y1 into x1 into alpha by 1 minus x1. So bring this term into this side, so we will get the y1, the minus will be plus y1, so x1 alpha by 1 minus x1 is equal to x1 alpha by 1 minus x1. So take the y1 common, when you take the y1 common, so when you take the y1 common, so we will get 1 plus, we get 1 plus alpha x1 by alpha x1 by 1 minus x1, 1 minus x1 is equal to alpha x1 by 1 minus x1. So now y1 is equal to multiplying now division, so alpha x1 by 1 minus x1 by 1 plus alpha x1 by 1 minus x1. So simplify it, we will get the finally y1 is equal to alpha x1 1 plus x1 alpha minus 1. So why are writing this means, if you know the relative volatility alpha, we know only you know the compound 1 mole fraction in the liquid phase. So if you want to know the what is the equilibrium mole fraction in the vapor phase, that we can know. So like in other temperatures, same we know only certain mole fraction in the liquid. So like we can easily determine from this expression vapor liquid equilibrium data. Okay, so we'll do this later. So with this so I will stop here. So with this we completed the vapor liquid equilibrium phase diagrams. Now next, in the next class we will see the liquid equilibrium phase diagrams and so on. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.